Okay, so now we are moving on to implicit differentiation. And to start off with explaining this, I'm just going to go with an example. So our first example is find dy dx when x squared plus y squared equals 1. Now, our equation, or our function we want to derive is x squared plus y squared equals 1. And if we were taking the derivative of this, normally, this x squared is not a problem and this 1 is not a problem. But now we have y squared. Typically when we're deriving, we have like y equals a bunch of stuff. We take the derivative, that will make dy dx equals the derivative of that bunch of stuff. But now we have y squared. So what do we do when it's y squared? Now, the thing to notice is we're finding dy dx. So let me first go over what this means, and then we can use this definition to actually solve or differentiate this equation. So when we have dy dx, that means to find the derivative, but with respect to x. The reason it's respect to x is because x is this second letter in the denominator. So whenever we're writing this dy dx notation, later on we're going to get a bunch of different letters. So we might have like dz dx, we might have dt dx, or maybe it'll be dy dx again, or dr dx. And that's a bunch of stuff. But the thing all of these have in common is that there is always going to be, it's like d a letter over d another letter. And the important thing you have to realize whenever we have this is that that second letter in the denominator, that is going to be the variable that we're going to, or that's going to be the letter that we treat as a variable when in our function. So if we go back to our original, we have dy dx, and that second letter in the denominator is x. So for our equation, we're going to treat x like a variable. And so that means if we're treating it like a variable, we could just differentiate it normally. So differentiating x squared, we will get 2x. And when we move on to y squared, notice y is not that second letter in the denominator. Because it's not that second letter, it's we're not going to treat it like a variable. And the thing when it's not that second letter in the denominator, we're going to treat it like a function. Any other letter in the alphabet, whatever it's going to be, we treat it like a function. So if we're differentiating a function squared, remember that's going to be chain rule, function to a power. So when we have function to a power chain rule, we're going to ignore whatever's in the inside, and we're just going to treat this like power rule first. So something squared, deriving that, we will get 2 times that something to the power of 1. In our case, that something is going to be just y. Now, what we have to do next is that outer function was the power, but now we have to differentiate the inner function because that's how the chain rule works. So the inner function is just y, and differentiating y, we get dy dx, as we've seen before in normal differentiating. And then on the right side, no matter if it's dy dx, dr dt, whatever all the other letters are, if you derive a constant, it's always going to be 0, so we can just treat that like normal. And now we are pretty much done with the hard part, which is the differentiating and identifying what we have to use respect to and stuff. So now it's just simplifying and isolating dy dx. So first, let's clean this up. It'll be 2x plus 2y dy dx equals 0. And now what we're going to do is subtract this 2x over to the other side and divide both sides by 2y, and that will isolate dy dx. And after doing that, we will get dy dx equals a negative y over x. Okay, I get that might have been a little bit confusing, so we're going to go through with another example. We're going to find dy dx again when x cubed plus y squared equals 17. So let's rewrite this equation so we have more room. And then we're going to look what we're finding. We're finding dy dx. And so notice the second letter in the denominator is x. So that means x is going to be our variable, and every other letter we're going to treat like a function. So our first term to differentiate is x cubed. Now notice it's x, we could treat it like a variable, so we just differentiate like normal, and we will get 3, or not 2, I wrote 2. We are going to get 3x squared, and then now we're going to move to our next term. This is y squared. Y is not x, and because x is what we're treating like a variable, y is not x, that means y is going to be a function. So hide the inside, because y is a function, and then so we have something to a power. Something to a power means 2 times that something, the power of 1, after we differentiate it. And then we differentiate the inner function. For us, the inner function is just y, and so it's differentiating that, we're going to get dy dx. Lastly, move to the other side where we have 17. Remember, as I said, whenever you differentiate a constant, no matter what it's with respect to, it's going to equal 0. And now if we just simplify this, clean this up a little bit, it's just going to, that whole mess is just going to turn into 2y dy dx. And now we could just do the same thing as before. Subtract this term to the other side, and then divide both sides by 2y. So that will give us dy dx equals negative 3x squared over 2y. Now in that those past two examples, you might be like, why are you stressing so much about like that second letter in the dy dx and stuff, the second letter in denominator? Why are you stressing about all that? It's always dy dx. And the reason of that is because it's not always going to be dy dx. This is something you might see later on in the future, so I'm just preparing you for that. So in this example, we have find dr dt when r to the fourth plus t cubed equals 40. So now we are not working with x and y, we're working with r and t. So let's go through that same process I said before. First, we're going to look at what we have to find and what it's with respect to. So I said that the second letter of the denominator of this d something is going to be the thing we treat like a variable. And in this case, second letter of the denominator is t. So t is what we are going to treat as a variable. Every other letter is going to be a function. So let's go through with this. So the first thing we have to differentiate is r to the fourth. Because r is not t, that means that r is going to be a function. So let's hide r. So r is just going to be something. If we differentiate something to the fourth, we get 4 times that something cubed. And then we have to differentiate by that something because that something is the inner function. So derivative of r is dr dt. Next, we are going to move to this term, which is t cubed. Notice that t is the second letter in the denominator, and t is what we're working with. So t is going to be the variable in this case. We can just differentiate it like normal, and that will be 3t squared. Lastly, again, we're differentiating a constant, so that's just always going to be 0. And now we're finding dr dt, so we could just isolate that. So we're going to subtract 3t squared to the other side, then divide both sides by 4r cubed. And then that just isolates dr dt for us, and that is our answer. Okay, so for the rest of the lesson, I'm just going to go with normal dy dx notation. So remember, x is going to be the variable for all this, and y is going to be treated as a function. So I'm not going to harass you with that anymore. We're just going to go with all the other things we need to worry about. So for this question, we have find dy dx of x plus xy equals y at the point 2, 3. So this is basically asking us the same thing if let's say we had like f of x equals 3x plus 2. This is like saying find f prime of 2, basically. Because we only care about the x value if it's like f of x. That's what it's asking. Find the derivative and then find it at this point. So that's kind of how we relate it to stuff we've done in the past. So the function we differentiate is x plus xy equals y. So now let's differentiate this implicitly. So derivative of x is the variable, so that's just going to be 1. Treat it like normal. And then now we have xy. And be careful here. Xy is actually a product, so we have to use the product rule for this. So product rule implicitly. So x is our first term and y is our second term. So we take the derivative of the first. Derivative of x is 1. Multiply by the second, so multiply by y. Then we add the multiply just the first, so that will just be x. And then multiplied by the derivative of the second. Now because y is a function, it's just we're gonna treat it like that, so it's just derivative of y is dy dx. And then lastly, that's gonna be equals, and then take the derivative of y, we just did that, it's gonna be equal to dy dx. Now let's get rid of all these parentheses I have here, so that will be 1 plus y plus x dy dx equals dy dx. So, this is something different. We have 2 dy dx's this time. Typically, in like the last 3 problems, we only had 1. So in this situation, what we're going to want to do, let's first move all the dy dx's to one side. So that will be 1 plus y equals dy dx minus x dy dx. We just subtract this x dy dx to the other side. And now what we could do is on the right side of the equation over here, we can factor out a dy dx. And that will leave us a 1 minus an x. And now from here, we can just divide both sides by 1 minus x. And that will let us find what dy dx is equal to. So now we have an actual function for what dy dx is. So I'm going to get rid of this work. Let me rewrite the function up here. So dy dx equals 1 plus y over 1 minus x. And remember, we weren't just trying to find dy dx for this one. It wanted it at the point 2, 3. So if we were had f of x equals blah, 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 and we wanted to find f of 2, we would just write f of 2 like this. But how do we write that in this notation, dy dx notation? Now the way we do that, if we were plugging in the point 2, 3, we would write dy dx, and then we're going to write that point in a subscript like this. So dy dx at 2, 3. Now if we actually plug that in to get our answer, we'll have 1 plus 3 over 1 minus 2, and that is going to equal 4 over negative 1 equals a negative 4. And that is our answer. Okay, now this new problem has two new things. First off, we're finding the second derivative, and second off, we're going to be finding a derivative of a trig function implicitly. So let's just hop right into it. What we're first going to do is just find the first derivative. So remember, it's all with respect to x, so differentiating the left side is easy, that's just 1. And the right side, this is chain rule implicitly. So first, just treat it like trig. What's the derivative of tangent of something? It's going to be secant squared of that something. And then we have to multiply by the derivative of the inner function. In this case, the inner function is y. Derivative of y is going to be dy dx. And that makes it actually really easy to isolate dy dx. We just divide both sides by secant x. So we'll get divide both sides by secant squared x, my bad. I'm misspeaking a lot. Divide both sides by secant squared of y. That's right there, yeah. So we get dy dx equals 1 over secant squared y. But remember, secant squared, or secant of anything, secant is just 1 over cosine. So if we have 1 over secant squared, that's just 1 over cosine squared, which just means this whole thing is equal to cosine squared. So cosine squared of y equals dy dx. And now what we do is we just take the derivative of this again. So let me clear some space first. Dy dx equals cosine squared y. Now, taking the second derivative, d squared y over dx squared, is going to equal, first we're going to actually rewrite this up here as cosine of y all squared, because now this will let us see it better. So first we're going to take the derivative of all of this, or this outside, because this outside is just power. So we're going to treat it like a power rule function or question first. So 2 times all of this stuff, which is cosine of y, all to the power of 1. Because power rule, it's just something squared, derive that, you get 2 times that thing to the power of 1. And then you have to multiply by the derivative of this inside. And this inside is going to be chain rule again, because it's trig. So trig of something, so derive cosine of something, and we are going to get negative sine of that something. And then so what we do now is look inside of this sign of something. Oh, that's y inside there. Y is a function again. So we have to multiply by the derivative of y now. And so the derivative of y is dy dx. So this was just kind of like a double chain rule thing here. But now we technically have what d squared y dx squared is equal to. The only issue is we have d squared y dx squared, but we also have dy dx. And that's not that great to have both of those in the same equation. We can actually fix that because we have a value for dy dx. Dy dx equals cosine squared of y. So let's just plug that back into our dy dx over here. So d squared y over dx squared is equal to 2 times cosine of y multiplied by negative sine of y multiplied by cosine squared of y. And now combining like terms, this negative times the 2 will be negative 2. The cosine y and cosine squared y, so this will be cosine cubed of y. And then this is just a sine y over here, so sine of y. And that is how we find a second derivative implicitly. Alright, to wrap up this overview with implicit differentiation, we have a 3-part problem to show you guys all the rest of the stuff you really need to know. So the first thing is part A. Find dy dx for this long equation. So it's not going to be that hard per se, just a bit tedious because of how long all this is. But it's basically all just the same topics that I have, both me and teacher in class have taught you. So implicitly differentiating this with respect to x. So 2y cubed, this is again just power rule. So bring down the 3, that will turn into 3 times 2 is 6, and then subtract 1 from the power, that will be a 2. And then the inner function is y. So 6y squared, but because y is a function, don't forget to multiply by the derivative, which is dy dx. Now we have this term, 6x squared y, and that is a product. Be sure to notice that. First term is x squared, second term is y. So, or the first term is 6x squared, I should say. So let's do product rule with this. The first part's 6x squared, that's really easy. That is just going to be power rule. And because it's a variable, we don't have to worry about multiplying by derivative of that. Next, we're just going to multiply by the second function. Then we add the first function, which is 6x squared, multiplied by the derivative of the second function. Derivative of y is dy dx. Next up, we have this next term, minus 12x squared. That's just power rule, and it's with x, so it's really easy. So minus 24x. Over here, we have plus 6y. And this one isn't too bad. It's derivative of y is dy dx, and then it's 6y, so it's going to be plus 6y, or plus 6 dy dx, I should say. And that is going to equal 0. So now let's keep all the dy dx terms on the left side, and then move all the non-dy dx terms to the right side. So doing this, we're going to have 6y squared dy dx plus 6x squared dy dx, and then plus 6 dy dx. Now we can let that equal to, if we were to subtract the non-dy dx terms over, we will have 24x minus 12xy. From here, we can factor out a dy dx. So dy dx equals, it's going to be all of these three, just without a dy dx. And after that step, we're just going to divide by whatever that thing is on both sides. So let's just combine both those steps into one. So dy dx is going to equal 24x minus 12xy. That's what's already over there. And then we're just dividing by this stuff, having factored out dy dx. So that is going to be 6y squared plus 6x squared plus 6. And then if we wanted to, notice all of these terms are divisible by 6. So we could say dy dx is equal to 4x minus 3xy. Wait, no, my bad. That's not dividing by 6. It will still be 4x minus 2xy over y squared plus x squared plus 1. And that is our dy dx. Okay, so that's part A done. Part B wants us to write equations of all the horizontal tangent lines. So remember, as we learned before, horizontal tangent lines are going to be when the slope equals 0, also meaning the derivative equals 0. And remember, all we care about is the numerator of the derivative equals 0. So that's going to mean 0 equals 4x minus 2xy. What we can do here is factor out a 2x. So 0 equals 2x multiplied by 2 minus y. And then divide both sides by 2. That just gets rid of that 2. And then now we actually have two answers here. We will have x equals 0, and we have that y equals 2. But what we want is the tangent lines. So to get our other coordinates for both these lines, what we're going to do is plug these back into our original equation. So our original equation is 2y cubed plus 6x squared y minus 12x squared plus 6y equals 1. So let me rewrite our points over here, x equals 0 and y equals 2. And let's plug these into here. So starting with x equals 0, that will be 2y cubed plus 6 times 0 squared, so this part's just going to be 0. Plugging in 0 here, that's just 0. So 2y cubed plus 6y equals 1. And this is actually something we can solve, but this is a calculator active question. So we just plug this into our calculator and solve for this. We will get that y equals, let me check, I forgot. Y equals 0.165. And so that would be our y value. So when x equals 0, y equals 0.165. We'll save that for later when we write our tangent line. Okay, now we're going to plug in our other points. So we just did that x equals 0, 1. But now what about y equals 2? So let's plug in y equals 2 to here. So 2 times 2 cubed, so that's 2 to the 4th, and that's going to equal 16. Plus 6x squared y, so y is 2. So that will be 12x squared. And then minus 12x squared. And then over here, plus 6 times y is 2, so plus 6 times 2 is 12, equals 1. These x squareds cancel. 16 plus 12 is 28, and 28 equals 1. That's normal, right? 28 equals 1? No, that's not true at all. But I didn't do anything wrong. So what it means is y equals 2 is not going to be an actual solution to this equation, so we don't care about that at all. So this first thing we found, x equals 0 and y is going to equal 0.165, this is the only points we care about for writing a tangent line. So if we go actually write our tangent line now, it's actually going to be a lot shorter tangent line than we typically do. So our typical form is y minus b equals m times x minus a for the point AB. Remember this? So let's plug our stuff into here. Y minus 0.165 equals m. Remember we are horizontal tangent lines, so the slope is 0. So m is 0. Multiplied by x minus 0. 0 times anything is 0, so this is all just 0. So pretty much we could just add 0.165 to both sides, and our tangent line is y equals 0.165. And that is our answer for part B. Okay, now part C. This one's not so nice, but it still works out. So, a line through the origin with slope -1 is tangent to the curve at point P. Find the coordinates of point P. So this one, it doesn't look like they give us two information, so what are we supposed to do with this? Well, they tell us that the line that's going to be tangent to the curve at point P has a slope -1. So let's just start trying to write this tangent line and see if we could go anywhere with that. So plugging in our information, we know that slope's -1, but we don't know actual x and y coordinates. Except we do. They give it to us subtly. It says a line through the origin. The origin. If you remember, the origin is just 0, 0. So that's our point. So basically it's telling us our tangent line is y equals -x. And what we can do to actually find the coordinates of point P is, remember how we plugged stuff back into our original equation earlier? Well, we can actually do the same thing here. But rather than plug in a point, we could plug in this formula, y equals -x. So let's plug y equals -x into here. So for here, it'll be 2 times -x cubed plus 6x squared times -x minus 12x squared plus 6 times -x equals 1. Over here, this will be a -2x cubed plus, or actually minus because the -x over here, so minus 6x cubed. And then over here we have minus 12x squared. Over here it's minus 6x, and that's going to equal 1. Minus 2x cubed minus 6x cubed is minus 8x cubed. Minus 12x squared minus 6x equals 1. And so this is another thing that you would pretty much just plug into your calculator. And if you did that, it looks like your answer would be x is equal to -1/2. And because of that, we know x is -1/2. We also know y equals -x. So that means that our y value is just going to be 1/2. Because a negative of -1/2 is just 1/2. And so that is how we deal with this not so nice problem. And that is pretty much the basis of what we learned in 2.4.